I'm going to go through some common pathfinding algos that I've been exposed to in the past. So some of these algorithms which I'm going to go over are DFS, BFS, and uniform cost search. And the assumption is that I assume you know what a stack, a queue, and a priority queue is. So for these different examples, I'm going to use this maze which I drew out. So the smiley face represents the start state, and the diamond represents the end or goal state. And these pink values here are the cost for every grid, and that becomes important later on. You could just ignore that for now. And you can see here that we're going to start with depth first search, and that it uses a stacked data structure behind the scenes. So it works by tunneling its way through one path until it reaches the goal state, and if the path it's tunneling through reaches a dead end, then it will backtrack and find the next available path to traverse through. And for these examples, the priority of movement is going to be left down, right top. It could be anything, but I just chose this priority here. So yeah, as I'm executing this algorithm, I'm going to use this stack data structure so that you can visualize what's going on behind the scenes. Yeah, so we could start this algorithm. So we first add 1, 1 to the stack because that's the start grid, because that's the starting coordinate. And then we just ask ourselves what's the first highest priority movement which we could take. And we could go left, so that's the movement we take. Then we ask the same question again, what's the highest priority movement? We can't go left, but we could go down because that's the second highest priority movement. Again, we ask ourselves the same question. We can't go left, but we could go down. And we could just keep going down until we get to 0.6. And when we get to 0.6, we reach a dead end. And as I mentioned before, with DFS, when you reach a dead end, it will have to backtrack. And the way it backtracks is by popping these coordinates of the stack until it reaches a grid where it can take a new path. So it's going to pop 0.6 of the stack. So it goes back up here to 0.5. And at 0.5 we ask the same question, can we take another movement? So we can't go left, we can't go down, that's where we just been, we can't go right because it's blocked, and we can't go up because we just visited that grid. So we have to backtrack again. And then on grid 0.4, we could see that we could take this path on the right because we can't go left, we can't go down because we just visited the down grid. And even if top was a high priority, we can't go up because we just visited the grid above. So we have to go right. And yeah, we just continue this pattern till we get to the diamond. And once we reach the diamond, we just have to reconstruct the final path. And to reconstruct the final path, we just connect these coordinates in the stack together. So we start at the bottom, connect 1, 1 to 0, 1 to 0, 2 to 0, 3. And you can kind of visualize that in the picture too. So we start at 1, 1, then go 0, 1, 0, 2, 0, 3, 0, 4. And you'll see that on 0, 4 we go to 1, 4 instead of 0, 5 because we popped these values of the stack as we had to backtrack. So we go to 1, 4 now, then 2, 4, and so on. And yeah, we could just reconstruct the final path like this. And we're done with that. But you'll notice that DFS doesn't guarantee the shortest path. because we could have taken this path here, but DFS couldn't identify that. If I changed up the precedence to right having the highest priority and then down having the second highest, then yeah, it would have found the shortest path. But that will only work for this specific maze, and it won't guarantee to find the shortest path in other mazes. So we need a better algorithm. Yeah, so DFS was 12 steps, but the shortest path was 6 steps. So now we look at BFS, and behind the scenes it uses a queue instead of a stack. And it works by expanding outwards layer by layer instead of tunneling its way through one path like DFS did. And by using this approach, you will guarantee to find the shortest path. And again, we'll just use the same precedence, which is left, down, right, up. So we'll just label the grids we visited with letters instead of the actual coordinates, because I think it's just easier that way. So in the beginning of the queue, we have the value A, which represents the start state, and then we'll just pop the front of the queue off, and that will be our current value. And then with this current value, we will explore its neighbors. So we look at the priority order again. So we first explore the left neighbor. We look at what the left neighbor is. We label it B and put it into the queue. We look at what the right neighbor is, label it C, put it in the queue. And we'll look at the top neighbor and label it D and put it in the queue. And you'll notice that the order matters here. So it's first come, first serve. So because B's in the front, we'll execute that one. And yeah, with queues, you can't just, when you add something like C in, you can't just put it in front of B, it has to be behind it. Okay, so once we explored all of A's neighbors, we will pop B off the queue, and that'll be our current value, our current grid. And then we just explore its neighbors and label them with letters again. So the highest priority is to look at the downwards neighbor. We label it E, and then the next highest priority is to look at the neighbor above and label it F. And we explored all its neighbors, so now we pop C off the queue, and it's gonna let it run without saying anything now. Yeah, so now it's reached the goal state. So we just reconstruct the final path, and that's what it looked like. So we found the shortest path, but it wasn't actually the most optimal path, because remember these pink values, these represent the cost of going to each grid, and if the pink value is higher, then it represents a higher cost, and if the pink value is lower, it represents a lower cost. And if the cost is higher, it means that it's not the most optimal path. So this green path here represents the most optimal path, because although it's not the most shortest, it's the most, it's got the least cost. So yeah, the BFS cost path was equal to 9, but the optimal path was 7. Okay, so why does cost matter? Let's say you had a short path with high traffic, and a long path with no traffic. Obviously, you're going to take the shorter path because it's got no traffic, and so it's going to be faster. So that's where cost comes into consideration. It considers these sorts of factors instead of just relying on the path length. Okay, so I didn't go through how BFS generated the final path, so I'm going to quickly go over that before I move on to this final algorithm, which is uniform cost search. So it works by using a dictionary to record the search path history. So I'm just going to give you a very small example to showcase this. And again, we'll use the same priority order as usual, left, down, right, top. So what I forgot to add in the previous example was this search path history dictionary, which records the grids which are connected with one another. And it will make more sense when we execute this. So for now, A is not really connected to anything, it's just none. And that'll be our base case for reconstructing the path at the end. So yeah, let's just run this through. So we pop A from the queue, and now A is going to be the current value. And then we look at A's neighbors, and we add B to the queue, and we also add B to the search path history, and we connect it to A because A is the one which found B. And we do the same thing with C, we add C to the queue. And for the search path history, we'll connect C with A because again, A found C. And that's all of A's neighbors visited. So we will look at B's neighbors now. So we put B off the queue, and that'll be the current. And then we look at its neighbors. So A is already visited, so we don't add that. But the grid on top is empty, so we will add that to the queue, label it D. And B found D, so that's what we'll put in the search path history. And then that's all of B's neighbors visited, so we will pop C off the queue. And then with C, A's visited, so we do nothing with that. But D is already in the queue, so we don't add it back. We don't add a second D into the queue, but we update its search path history. So instead of D now, we replace, instead of saying B found D, we're going to say C found D, like that. And then also I just added E to the queue, and I said that E found C. I meant C found E. And then that's all of C's neighbors visited. So we will look at we'll look at D now, and we look at D's neighbors, and the only one we could really look at, the only grid which we could really look at is the one on top, because everything else is visited or blocked. And yeah, we get to the final grid, which is F. And then after that, we could just end the algorithm. And then yeah, we could just reconstruct the final path now. So we look at the search path history, we look at the goal grid, which is F, and we'll just connect them up. So we see that D found F, so we go to D. Then we say, okay, C found D, so we go to C. And then we say A found C, so we go to A. And then A's connected to none, which is the base case. And then yeah, down here's what the final path will look like. F to D to B to A to none. And when we get to none, we could just end it there. Okay, so now we could just finish this off with a uniform cost search. So this is the algorithm which also considers cost to find the most optimal path. So it's like BFS, but it considers cost. And yeah, it uses a priority queue. So along with putting the node in the queue, we also put its corresponding cost into the queue as well. So this is what the priority queue will look like in the beginning. We put grid A into the queue, the starting grid, and we put a cost of 0 in because again it's just the starting grid. Then we pop A off, and then we add its left neighbor first because left is the highest priority, and you can see here that the value on the grid is 1. So that's what we put in the priority queue. Then we'll just explore all of A's other neighbors. And then once we've finished with A, we'll pop B off. And then with B, we will explore its neighbors. And you'll see that although the grid on F is 1, we have that the cost here is 2 in the priority queue, and that's because we add up its predecessor's value as well. So B's value was 1, and then we add F's value, which is also 1, so it's 2. And that's the same with E as well. B's value was 1, and we add E's value 2, so that's 2. And you also notice that if this was a BFS search, or if this was a normal queue, E and F would be at the back of the queue. But because this is a priority queue, the queue is prioritized by cost. So E and F could push in front of D because it has a lower cost, meaning that it's got a high priority. And that's why it's called a priority queue. And yeah, I think there's not really much else to explain here, so I'm just going to let it run by itself. And once it's found the final path, it will generate it, and it will use a similar strategy to the BFS version. So it uses the same approach, and you'll end up with something like this. And yeah, those are the 3 algorithms which I wanted to talk about.